Before we get into our next example, I want to define a term that you might hear, which is statistically significant. We define statistically significant as the idea when our observed results, in other words, the sample statistic, are unlikely, assuming the null hypothesis was true. When the observed statistic is unlikely given the null hypothesis, we would say that that results in something that would be considered statistically significant. In other words, it's unlikely for us to have something like that happen if the null was really true, and we reject the null. If we're rejecting the null, then that is a statistically significant concept. So let's move on and talk about another example here. In this example, we're talking about the color of uniform competitors used during their Olympic events. So this is specifically referring to combat sports like boxing, taekwondo, and so forth. And it was noticed that the wrestlers were randomly assigned either red or blue uniforms. For each of the matches in the 2004 Olympics, they recorded the uniform color of the winner. So out of 457 matches, they found that those competitors wearing red won 248 times, whereas those that wore blue won 209. The people that conducted this study wanted to know whether or not competitors wearing red had an advantage over blue. And then we're going to use our level of significance at 0.05 to determine that. So the first thing we need to look at is we always have to verify our parameter. We're going to verify our parameter. We're going to identify our parameter. We're going to verify the normal distribution, and then we're also going to make some statement about that population. So what's the parameter we're interested in here? The parameter that I'm looking at is a proportion. I want to know, does a red uniform competitor have an advantage? So the proportion of times a red uniform wins, if there's two outcomes, you either win wearing red or you don't, then that becomes a 50-50 chance. So you've got red being our interest here. We think red is going to have an advantage. And there's two outcomes. Wearing red either wins or they don't. So it's a 50-50 chance. To verify the normal distribution, we perform our NP1 minus P calculation, and we can see that it is greater than or equal to 10. So we're good. Now, what's our statement about the population? Remember, this is the claim, or this is our null and our alternative hypothesis that we want to develop. The null hypothesis, that statement of equality, the part that we always assume to be true, would state that the probability competitors wearing red uniforms win is just 50%. Or in other words, symbolically, H sub 0 says that P is equal to 0.5. The alternative is what we want to show. It's what the researchers believe. Researchers believe that competitors wearing red have an advantage. So the probability that competitors wearing red uniforms win is more than 50%, or in other words, H sub A says that P is greater than 0.5. So we have our beginnings here of our hypothesis test. The next idea is that we collect the evidence. So we saw that they looked at 457 matches and found that 248 times the red wearing competitor won. So we would see that the number of successes X of winners out of 457 trials resulted in the proportion of winners from this sample at 54%. So that was the sample that they saw, that 54% of the competitors that won were wearing red. This is why they're kind of thinking that maybe red red uniforms are advantageous. So we need to go in and analyze the data. When we analyze the data, we're going to use technology using StatCrunch to. So since this is a proportion parameter, I'm going to go to stat, proportion stats, one sample with summary. The number of successes for the red competitors was 248 out of 457 trials. Again, our proportion of times that you win in the long run that we assume to be true is just zero point 0.5. We wrote this already. And then we want to show that it is actually more than that. When I hit compute, StatCrunch gives me an output window that looks like this. And we can see in the very last column over here, our p-value. Our p-value is 0.0341. And because the p-value is less than 0.05 alpha, our conclusion would be to reject the null hypothesis. So how do I state my conclusion? Remember, if I reject the null hypothesis, then I'm actually in favor of the alternative. So we would say that there is sufficient evidence to support the claim that competitors wearing red uniforms win more than those wearing blue. In other words, red does have an advantage over blue. So our hypothesis test for this example, do red competitors or do competitors wearing red have an advantage over others? We would say yes, there is a claim, or we do find evidence that supports that claim, and we would say that this would also be statistically significant. Now, what if we look at that exact same example where we're talking about red versus blue uniforms, but this time we see that the researchers don't really have an idea or don't really think that red wins more often, but they also don't think that blue wins more often. So we're going to use this same information, but maybe we are going to approach it differently. I don't know whether one has an advantage over the other. So let's restate our null and our alternative in terms of this different question. We would say that the probability that competitors wearing red uniforms is 50%. So our null hypothesis is not changing, right? We are still assuming it's a 50-50 chance that you're going to win wearing red. However, the alternative does change, that the probability competitors wearing red wins is not 50%, changes the inequality symbol we see here in our alternative. So now we need to go back and rerun our test with that different inequality. So if I come back to StatCrunch, still using our one sample proportion where the number of successes didn't change out of the observation, the only thing I really need to change is this inequality symbol here so that p is not equal to 0.5. When I hit compute, we'll have a p-value show up in the last column. So our p-value, which is a 0.06 or 0.07, the probability of getting our sample of 54% red winners is greater than our alpha of 0.05. So because p-value is greater than alpha, we fail to reject the null hypothesis. If I fail to reject the null, I'm keeping the null. So when I state my conclusion, if I keep the null, I'm actually going to throw out the alternative. we would say that there is not sufficient evidence to support the claim that competitors wearing red win more often. Remember that our conclusion, when we are failing to reject the null, or in other words, when I am keeping the null, the conclusion is always stated in terms of the alternative. So this conclusion says that I don't have enough evidence to support the alternative, and that's how we state it. Now, notice the difference between the two examples we did here. In example 4, we were talking about a claim that red wins more than 50% of the time, which is what we were assuming. And in this example, we just didn't know who won more often. So we're comparing actually in example 4 a right-tailed test or a single-tailed test to this example here with a not equals, which is a two-tailed test. And the probability on a two-tailed test, or the p-value on our two-tailed test of 0.07, is actually twice as large as that p-value on our single-tailed test. And when we see that, we'll start to notice that, in other words, if you're running a two-tailed test, you are actually going to be asked to provide more evidence to throw out the null. It makes it harder for us to just throw that null hypothesis out when we run a two-tailed test. So a two-tailed test provides less evidence against that null, right? So if I have less evidence against the null, it makes it harder to throw that null hypothesis out. So you better have more evidence, in other words, for us to just throw out that original claim. These two-sided tests, therefore, are what's more often used in scientific practice because it makes it harder for us to just throw out that original claim.